Okay, yesterday we have reached this rabbit and fox problem. I mean, in last lecture, up to the point where we have got solution of first differential equation, which was log p plus radical 1 plus p square is equal to log x by c raised to k, where k is your ratio a upon b and c is starting point x coordinate. Now, how did we achieve this? By substituting initial condition p is equal to 0 when x is equal to c, because this is c comma 0 and the rabbit starts from here. Therefore, when time t is 0, the slope of tangent is 0. So p is equal to 0 if x is equal to c. If we substitute this, get the value of our first integral constant of integration, and then we get this result. This is first order, first degree differential equation, which we can write. If we solve it for p, we will get it like dy by dx is equal to half inside bracket x by c raised to k minus c by x raised to k. Okay. First check whether you have arrived at this step, and maybe then we go ahead and integrate it. Okay. So I assume to this point, and therefore if we integrate both sides, we get 2i is equal to integral x raised to k upon c raised to k dx minus integral c raised to k upon x raised to k dx, which gets converted into easy x raised to k plus 1 upon k plus 1 times c raised to k minus x into 1 minus k upon 1 minus k times c raised to minus k plus some integration constant c2. c1 already evaluated. Now what is the condition here to deal with this? Y is equal to 0. Put y is equal to 0 if x is equal to c, right? And therefore you will get c2 is equal to c upon 1 minus k minus c upon k plus 1, which is equal to 2kc upon 1 minus k square. Understand all this. If there is any error from my side, point it out. Otherwise, this is what. So, equation is the equation of the curve. That is what we are asked to do. Trace the path of the fox. 2i is equal to x raised to k plus 1 upon k plus 1 c raised to k minus x raised to 1 minus k upon 1 minus k c raised to minus k plus 2kc upon 1 minus k. This is the curve which fox will follow. Okay, now we have to cross check whether this is correct, at what distance rabbit hole should be so that he is safe. If a is less than b, then if a is greater than b, that means the value of k. If value of k is less than 1, then what? So case 1, if A upon B is equal to K and suppose if A upon B which is equal to K is greater than 1, what do we interpret out of this? If K is greater than 1, can we look at this and find out what will happen? Just think about it and explain. Okay. So once we get this particular equation, we are supposed to discuss two cases. If K is greater than 0, we will observe that RHS as x tends to 0 will tend to infinity, and therefore rabbit will run away and fox will not be able to catch him. So rabbit is safe. In case 2, if K is less than 1, then as x tends to 0, first term is 0, second term is 0, then we get distance y is equal to Kc upon 1 minus k square. If the rabbit hole on y-axis is at lesser distance than this quantity, k upon 1 minus k square times c, whatever distance is the starting point of fox, its ratio, corresponding ratio k upon 1 minus k square. If your rabbit hole is there, then your rabbit is safe. Otherwise, a rabbit will be caught by the fox. That is the case 2. And now we are supposed to consider if they have equal speeds. So case 3, A is equal to B. Then what? Explain what if A is equal to B. Okay, if K is equal to 1, then we have 1 minus K in the denominator at this stage. Therefore, it becomes the equation which is not correct. The equation of the curve which we are getting is not correct. However, we got it by 2 times integrating, but then whenever we put 1 minus K in the denominator, we will have to cross check that step, and hence what we will have to do is we will have to look at the differential equation which we have solved. So if K is equal to 1, then original step dy by dx is equal to half x upon c minus c upon x. This is what is the differential equation that you have which you need to solve, and as you were saying, there will be a long term involved in it when you solve this differential, but then I will take you what do we mean by this. Okay, now understand what I am trying to say. Dy by dx is slope at a local point, correct? But it is distance traveled, it is slope, so distance traveled. What is dy by dx? When delta x is very small, not equal to 0, delta x, distance traveled in the direction, in the positive direction of y-axis per unit distance traveled in positive direction of x-axis. That is our slope, correct? So if I multiply by the distance traveled in the direction of x-axis, then what is the meaning of x into dy by dx? So x is the distance traveled in the direction of positive x-axis. So if I multiply by the distance traveled to the slope, I will get the distance traveled in the direction of y-axis. Okay, so we need not have to actually integrate this. Here itself we can interpret it in better way. Limit as x tends to 0. So I'm multiplying this entire equation by x. So x dy by dx is equal to half x square by c plus minus c, multiplying it by x, and I am interpreting this as, say, I mean, when delta x is very small, okay, this is supposed to be dy, this is supposed to be dx, and then when you want this is the distance. Now at this point the fox is going to be there, at this point rabbit is going to be there, something like that, and then the tangent slope is dy by dx, which is correct. So we are interested in this d, which is going to be a radical of this plus this, and therefore what I am trying to show you is this, using this diagram, and when differential x is very small, this is the distance between both of them. That is what I am trying to bring it to your notice. This is the distance between the both of them, and as because their speeds are equal, I mean, as x approaches 0, practically they are going to be parallel lines. I mean, this is the curve and this is y-axis. So rabbit is running along y-axis and fox is running along the curve, but when x tends to 0, they are going to be asymptotic to each other and they will never intersect. However, after some time, the distance between them will be almost constant because this line is very close to y-axis. They are parallel lines almost for all practical purposes. And therefore, their distance between them is going to be constant. And as x, so we will have to evaluate this limit x tends to 0. As x tends to 0, the distance between them is going to be equal to minus c by 2. As x tends to 0, distance. So for a numerical purpose, it is c by 2. Okay. So they will keep running behind each other by keeping distance c by 2 if their speeds are equal. Now, this is little involved for understanding, but you can, I mean, here is the explanation. If I know my speed, if I know my speed, if I know the slope, distance traveled in positive direction of y-axis per unit distance traveled in positive direction of x-axis, and if I know how much x-axis I have traveled, then I will come to know what is the distance in positive direction of y-axis that I have traveled. Now, this dy, I am practically taking this dy and this d same because delta x is very small. Delta x is very small, x is tending to 0. Okay, and that is why this is a legal identity, which is distance between them, and if you split up that as x tends to 0, you get this term 0, and you end up getting distance between them as minus c by 2. That is what is the distance that they will maintain, keep running one behind the other when their speeds are equal. Green. Question 2. Word problem. Question 2. 4 bugs sit at corner of square table. Of side, what am I taking? The side A. Sorry, of side root 2A. That is the side of a square table. At the same instant, they will begin to walk. With the same speed. Each moving steadily towards the bug on its right. If polar coordinate system is set, I mean both polar as well as around the diagonal path of the curve that starts from the distance bound. Okay, now let us not write it. So that is what is the setup. And more than writing, what we are doing is, this is what is your y axis, this is your x axis, and you have a square table looking like this. Okay, this is a comma 0 and therefore side is root 2a. Okay, and now you have a bug at 4 places, 4 corners, here, here, here and here, and this will start moving by looking at this. This will start moving by looking at this. So if at any time t, if this bug has reached here, then correspondingly this bug will reach there. All of them will follow some symmetry. Correct? Correct? Is this correct? Yes. Am I supposed to do it like this? Okay, so now basically XY system as well as theta system, we are supposed to do this. So what we are supposed to do is trace the path of the bug. I mean bug number 1. This is first bug. Trace the path of a bug. And eventually I think we should find out the total distance traveled. Also find total distance traveled by a bug before they meet each other. So, okay, I hope your problem statement is understood. After any point t, suppose the coordinates of this point P is x comma y, four bugs, x comma y, then what are the coordinates of this point? That is most important to write. This is suppose Q. Now this distance is x and this distance is y. Okay, so this distance x is going to be over here, this is going to be distance x, and this distance is going to be y here. Okay, so coordinate of this is going to be minus y comma x in terms of xy equirate. Numerically it is going to be like that, and whatever curve you have traced so far, at that point this is going to be tangent. Correct? Therefore dy by dx, slope of that tangent is equal to what? X y minus x upon y plus x. This is the differential equation that you have, which if you solve, you get relationship between y and x. Now, I think something like this we have already solved. So from here you should proceed and get the equation solved. I mean, it is as simple as that. Put y is equal to Vx because it is homogeneous, and therefore dy by dx is equal to V plus x dv by dx. Okay, so dy by dx is V plus x dv by dx is equal to V minus 1 upon V plus 1. This gets further simplified as x dv by dx is equal to V minus 1 upon V plus 1 minus V, which is equal to minus of 1 plus V square upon 1 plus V, which is equal to x dv by dx, and it is now variable separable. Therefore, you get V plus 1 upon V square plus 1 dV is equal to minus dx upon x. So now you will have to solve this by separating. So it is an easy integral, V upon V square plus 1 plus 1 upon V square plus 1, and therefore after integrating you end up getting half log 1 plus V square plus tan inverse V is equal to minus log x plus C1. When y is equal, initial condition, when y is equal to 0, x is equal to a. So if we substitute this, we get C1 is equal to log a. And therefore, our equation is tan inverse, solution is tan inverse V is y by x plus half log inside bracket x square plus y square upon x square, that is 1 plus v square, is equal to minus log x plus log a, which is a upon x. Minus log a x plus log a. Okay. So for all practical purposes, you have log at 3 places and tan inverse x by x, y by x at 1 place. So therefore tan inverse y by x is equal to log a upon radical x square plus y square. I am jumping few steps, but then you can deal with this and get it, which is good. And now here itself, if you consider y by x is equal to tan theta, y by x is tan theta, and radical x square plus y square is equal to r, then this is theta is equal to log a over r, which is r is equal to a e raised to minus theta. That is your polar equation. This is your Cartesian equation. So that is the path which will be followed by the bug, by traveling such that they keep looking at the bug at right. Now, if we have equation in r theta, we can find out the length of the curve. That you can do it quickly and maybe copy this also, and then we will get into better understanding and generalizing. Length of the curve, I think the formula is easy. If you remember the formula, it is integral theta 1 to theta 2 radical r square plus dr by d theta bracket square d theta. So basically for us it will be integral 0 to infinity. I mean, they will keep on rotating eventually as they come closer and closer, and therefore the angle will tend to infinity. Inside bracket r square is a square e raised to minus 2 theta plus dr by d theta. Dr by d theta we can, I think, calculate orally, and you can put it a square e raised to minus 2 theta again d theta. This is going to be your curve length. Uh, and inside radical it is there, so it becomes 2a square inside radical becomes root 2 times a integral 0 to infinity radical e raised to minus 2 theta. So e raised to minus theta, square and radical will get cancelled, is equal to root 2 a integral 0 to infinity e raised to minus theta to theta, which is equal to root 2 a integral 0, not integral now, you have to evaluate at some point of time, and it is minus e raised to minus theta to be evaluated between 0 to infinity. If we put infinity, it becomes 0. If we put 0, it becomes 1. So answer is minus minus 1. Therefore, root 2 times a. That is the distance that they will travel before they reach at center. Okay. Now, if we want to generalize this, we will have to develop a small formula which I will explain you now. समजा शेवटचा फॉर्म्युला दाखवतोय बघतो दाखव r is equal to now understand this situation, very important. We have y and x and we have a curve, something like this. Okay, and when it comes to polar form, suppose you are considering this point, starting point, and you are drawing a tangent to it. Okay, no, this is bad. Let me draw tangent, something like this. But if the vicinity is very close, then the curve and tangent. Okay, green is the tangent. Now this is your R. And this is your theta as far as this point P is concerned. After some time, you move delta theta. This is delta theta. Okay, And if you keep r same, then it is going to be arc. Why I am doing it like that? If our delta theta is small and r is same, then this is going to be arc. Okay, and then you are considering the next point after theta, delta theta, and that means you are on the curve here. Okay, and the tangent and the curve, there is a little gap, because as your delta theta tends to 0, tangent and the curve will be almost same. Now if we extend this r wala line, then the angle between the tangent and line joining center with P, suppose that angle is phi. Okay, and uh, the angle here from, now wait me, I have a facility to expand and make it bigger. Okay, now this angle is psi. Okay, what is phi? Phi is this angle. That angle is psi. How much is this length? This length is r delta theta. And how much is this length? It is delta r, increase in the radius. Okay. So if I write a tan of psi, that is, consider this as a right angle, because even if this is arc, it is as good as straight line. When delta theta is very small, this is very small, and therefore tan of psi, this is going to be 90. Tan of psi is equal to r delta theta upon delta r. Okay, and as delta theta tends to 0, psi equals phi, because as this angle between these two rays is going 0, that means they are parallel rays, and therefore these two psi and phi become alternate angles, and therefore they are equal. Okay, that is what is the situation, and therefore tan of phi is equal to r, tan of phi is equal to r d theta upon dr in limiting case. This is important for me. Now we can come back to this if you have not understood, but let me finish. Now we have been given n-sided regular polygon. This is the starting point. Say first triangle is like this, isosceles. This is the second position of second bug. Okay, and it is n-sided regular polygon. So after some time, what will happen is, after some time you will go, it should not be bisector. After some time, what will happen is, this bug will reach somewhere inside. It is not going to be on that line, it will be somewhere inside, and corresponding next bug will also be there. So it is going to be yet another next level isosceles triangle. So this is original position I am writing. This is second position of the bug, I mean at after some time t. So if you compare this diagram with this right now, this angle that we have, this angle, I mean this angle, this is isosceles triangle and this is your R wala line joining P. Okay, this angle as per this notation is phi, correct? So I mean here also it is going to be phi because it is always going to be the same, because this is isosceles triangle and every time this vertex angle is going to be equal. I mean if it is blue also it is equal vertex angle, and if it is green also it is equal. So can we suppose this is n-sided polygon, n-sided regular polygon, and this value is phi. And can we find out phi in terms of pi and n? I think so. Phi is say x, this is x. Phi is equal to 180 minus or maybe pi minus x. Okay, but how much is x? X is 90 minus whatever the central angle is. Central angle at center, let us call that angle say alpha. Alpha is going to be equal to 2 pi upon n. Okay, so x is equal to pi minus 2 pi upon n whole divided by 2, correct? And therefore phi is equal to pi minus 2 pi upon n whole divided by 2. I hope you will be able to simplify this and you will get pi by 2 plus pi by n. Phi is equal to. This is the value of phi that you will have. And therefore, by this equation, if we go, we will get our direct differential equation. Tan of pi by 2 plus pi by n, that is tan phi, is equal to r d theta upon dr. Now tan of pi by 2 plus pi by n is minus cot pi by n. And this is simple equation to solve. Simple differential equation. Solve and get the function. Solve and get r is equal to what? That is your generalized. And we can put that generalization n is equal to 4. We should get our original equation. If we solve this differential equation, which is relatively easy to solve, we will get equation r is equal to a e raised to minus theta tan pi by n. That is the equation of curve. What is a? A is the starting point. When r is equal to a, when theta is equal to 0, r is equal to a. That is the initial condition which will be helpful to you to evaluate the integration constant, and your curve is going to follow this. Now if it is pi by 4, tan pi by 4 is 1, therefore we end up getting this equation for square. Okay. Now if you solve for length of the curve between 0 to infinity, you should get length of the curve you should end up getting eventually answer as a cosec pi by n. Okay, so if n was 4, cosec pi by 4 was root 2. and therefore answer was 4. So let us just tabulate whatever we have found out. These are the two general formulae. Therefore, if n is equal to 3, the length of the curve is going to be 2a upon root 3, and the side length, that is, it is going to be equilateral triangle, and therefore length of the side is root 3 times a. If n is equal to 4, we have root 2a and root 2a, both same. If n is equal to 6, that is, these are our special cases, length becomes 2a and side length becomes a. Shall we try n is equal to 2? I mean, it is a segment, x-axis. One bug is sitting here at distance a, another bug is sitting here at distance a, and they start traveling to each other. Of course, they will meet at origin and they are supposed to travel distance small a. But then, are we getting it? If n is equal to 2, cosec pi by 2 is 1 upon sine pi by 2. I don't know.
Yes, sir.
Sine pi by 2 is 1, and therefore length is a. Okay. And what is the side of this regular polygon with two sides? A by 2. I mean, that doesn't make sense. This does not make sense. But we get it. They have to travel half the distance if it is a two-sided regular polygon. Exaggerating, but this is wonderful achievement. This is great. And those equations are so nice and simple, easy to remember. Okay, so before I get into the singular solution, I have got one more differential equation which you should know how to solve. Solve d2y by dx square plus dy by dx minus 6y is equal to 0. Suppose we want to solve this, and there is a specific method to solve this. I mean, easy method. Maybe I will explain it to you directly, or if you have come across, then only you will solve by that method. And it is as follows. Let y is equal to e raised to rx. Therefore, dy by dx is equal to r e raised to rx. Therefore, d2y by dx square is equal to r square e raised to rx. Correct? And hence, if we substitute this back into our equation, we get r e raised to rx common inside bracket, r square plus r minus 6 is equal to 0. And therefore, we end up getting r is equal to 2 and r is equal to minus 3. Okay, so y is equal to e raised to 2x or y is equal to e raised to minus 3x. That is what we have reached by doing this so far. However, the solution of differential equation is written like this. Y is equal to a times e raised to 2x plus b times e raised to minus 3x. Now, why from this step to this step? Why? Experience. Okay, so if this is our solution of this differential equation, then we cross check whether we get back the original equation. So we differentiate this. Dy by dx is equal to 2a e raised to 2x minus 3b e raised to minus 3x. d2y by dx square is equal to 4a e raised to 2x minus minus plus 9b e raised to minus 3x. Add them. So d2y by dx square plus dy by dx is equal to 6 inside bracket a e raised to 2x plus b raised to minus 3x. Oh my god, this is equal to 6y. And hence we get the original equation. It is degree 2 equation, order 2 equation, degree 1 but order 2 equation, and therefore we want two constants which we have here, and therefore this is the solution. Okay, now in general, d2y by dx square plus p dy by dx plus qy is equal to 0. If this is the form, then it is the future of this will depend on basically quadratic equation r square plus pr plus q is equal to 0. Like here the quadratic equation was r square plus r minus 6 is equal to 0. So discriminant of this was greater than 0, this quadratic, and therefore we got two distinct solutions. Okay, so depending upon p square minus 4q, if greater than 0, two distinct solutions like this, and the final solution will look like y is equal to a e raised to r1x plus b e raised to r2x, where r1 and r2 are the roots of this, if both are real. Case 1. I'm just running through it because it is a special type of differential equation which fits into our syllabus, but we are using some altogether different method. Case 2. P square minus 4q is equal to 0. Then what will we have? Y is equal to a e raised to whatever r x plus b x e raised to rx. Now these are some important things, because I cannot write b e raised to rx, then a plus b is going to be one constant, and therefore maybe we will look at this case in detail by taking an example, say d2y by dx square minus 10 dy by dx plus 25y is equal to 0. Okay, so r is equal to 5. That is what we get if we solve the quadratic in r, and therefore we get y is equal to e raised to 5x by the work that we have done. So if y is equal to e raised to 5 is the solution of this differential equation, then y is equal to x e raised to 5x is also the solution of this differential equation. That is what is the finding. Okay, and hence you combine these two solutions to get the general solution. You can cross check whether e raised to 5x y is equal to e raised to 5x is a solution of this differential equation, and by putting specific values of a and b we will get that. Then y is equal to x e raised to 5x is also solution of this differential equation. By putting suitable values of a and b we will get that solution, specific solution. And therefore if p square minus qx is equal to 0, you need to remember that this is what is the solution of the given differential equation. And if case 3, p square minus 4q is less than 0, then what are we going to have? It is same as first, but then you get into complex numbers. So y is equal to a e raised to how do we write? A e raised to some complex number c, a e raised to cx plus b e raised to c bar x. That is what it comes down eventually. Maybe we can cross check, but then I mean this is one of a kind. If you remember it, your purpose will be solved. And then if you simplify it further, it will be e raised to a real part and etc. So maybe if we take one example, d2y by dx square minus 4 dy by dx plus 13y is equal to 0. Okay, you can solve this and show me what is your solution of this differential equation. And I think the discriminant is less than 0. So how will you go about it? Discussion on singular solutions. Let me first give you an example. What do we mean by singular solution and how do we get it is the next story. Essentially, uh, f of x comma y comma p is equal to 0 was our differential equation, and f of x comma y comma c is equal to 0 was our solution. Okay, now here x and y we know their places are same. X is independent variable, y is dependent variable in both the places. However, the c parameter here is basically in the solution. C parameter is basically deciding the family. Once the nature of the curve is fixed, for different values of c you will keep getting different curves, and that is what is the purpose of this c. Okay, in fact p also is exactly the behaving exactly like c here, but it is at one level up, which is at differential equation level. So this is also a parameter. For different values of p you will keep getting the different natures of the differential equation. Okay, that is the first thing that we need to understand. Now suppose I give you a differential equation, simple differential equation, y square inside bracket 1 plus p square is equal to 1. Suppose this is the differential, p is over this p, so it is a relationship between x is not there, so y and p, and if you solve it for solving for p, then you will get p is equal to radical 1 minus y square divided by y. Okay, and integrating it you will get, this is p is dy by dx, and therefore after integrating you will get x plus c bracket square plus y square is equal to 1. You may cross check very quickly whether you get the same answer or not, but you will end up getting this answer, and this is our arbitrary constant, and we know for sure that these are the circles. These are the circles, and all of them are of radius 1, and maybe I will try to draw them. What is this C now? C is the coordinate of the center, x coordinate of the center. This is x-axis. Okay, so there will be all congruent circles with different values of C you will have over here. Okay, and that is what is the solution of given differential equation. Okay, now if we put y is equal to plus or minus 1, y is equal to plus or minus 1, will this satisfy the given differential equation? Let us cross check. P is dy by dx. If it is plus minus 1, then dy by dx is 0, and hence this bracket is 1 and y square is equal to 1, and yes, it satisfies. So y is equal to plus or minus 1 satisfies the given differential equation, and therefore we have to consider it as one of the solutions of differential equation. But it does not have a constant c, so it is not a family of curves, it is specific curve. In this case, if we observe, it is this line. I mean, all my circles, you have to assume them as congruent circles, and this line which I am drawing is supposed to be the tangent. This is y is equal to 1 and this is y is equal to minus 1. Okay, and these two lines also satisfy the original differential equation. Now geometrically, let me explain you, and then I will go to algebraic explanation. Now if I consider two circles which are, if I consider two circles, and I think I should be able to copy it and bring it very close to, that's like slow internet, or this wide word is slow. Copy, paste, HMI. It takes a lot of time every time. Instead, I should, what is this? This is copy, come here, now I should come here and right click, paste, good. So now I am supposed to select this and move it. Okay. Array, come out. So these are the two circles which I am considering. This is x-axis. Okay. For some value of c, this will be first circle. For some other value of c, this will be second circle. And there is a substantial gap between their centers. But then, now you have to consider a limiting case when this C2 starts coming closer and closer to C1. Maintain a gap, but they start coming closer and closer to C1, and then at the same time, suppose at this point, if you observe the tangent to the circle, it is horizontal, y is equal to 1. The other circle also, it is the same tangent, y is equal to 1, and hence when these two circles are coming closer and closer and closer to each other, then those points where we are considering those tangents are also coming closer to each other, and the tangents to the curve and tangent to the y is equal to 1 line, it is one and the same. and therefore y is equal to 1 line also satisfies the original differential equation, because at this point the slope of tangent is 0 for C1. At that corresponding that point, slope of tangent to C2 is also 0, and now C1 and C2 are coming closer to each other. Therefore that tangent is not moving and it is one and the same tangent, and hence the locus of this point, which is supposed to be very near to each other, and corresponding tangents at that point, they all coincide, and therefore eventually y is equal to 1, and same thing will happen to y is equal to -1, and these two lines eventually satisfy the differential equation because all the three things coincide there. And therefore this particular red line, I mean these two lines, we will call envelopes of the curves which we have got otherwise. By changing value of c, the curves that we have got, uh, these two lines, or maybe a singular solution which we get, if it is equation of an envelope, then it envelopes those curves, all those curves. Okay, so looking at what is exactly happening here, when in limiting case, when I am bringing these two circles closer to each other, the C value, or maybe the delta C value change in this constant, arbitrary constant, is tending to 0. This is important to know, that delta C is tending to 0, and C is my arbitrary constant, and that is providing me the spatial solution as delta C tends to 0. Okay. Now let me take you to the theory of discriminant. We have studied ax square plus bx plus c is equal to 0, f of x. This is our quadratic equation. And we say that this quadratic equation has got, say, repeat root. Alpha is a repeat root. That means if you substitute alpha in this equation, of course you will end up getting 0. But our theory says that the discriminant of this equation, b square minus 4ac, should be 0, then alpha will be one more time root. That is what we have done it by method of completing square, etc. But now we wish to do it by different method. Alpha is a repeat root, and therefore instead of this 0, suppose I write is equal to, what is this f of x? What is this f of x? It is x minus alpha bracket square times some g of x, because alpha is supposed to be the repeat root. Okay, so what is f of 0? Sorry, what is f of alpha? F of alpha is going to be 0, because if you put x is equal to alpha here, you end up getting this quantity equal to, this quantity, if anything is equal, that 0 I have removed. So at the moment you put alpha, it satisfies the equation, and therefore f of alpha is going to be 0. But then this repeat root, you must be remembering when we were in 9th standard, and when we were given that we were trying to use our factor theorem and putting those factors. Suppose we put 1, then x minus 1 is a factor if we get 0. If we put 2, and if we get 0, x minus 2 is a factor. But then we were having trouble when we said 1 is factor of the given polynomial 2 times. And at that time, we had to remove x minus 1, find out what the remaining quotient polynomial is, and then put x is equal to 1 in that polynomial to check one more time whether it is root or not. And that was a little difficult at that time, because finding out that quotient was not easy. You had to actually perform the long division to find out that quotient. and in the quotient polynomial, you have to substitute the repeat root again and check whether it is 0. Then we concluded that yes, x minus 1 bracket square is a factor of given polynomial. Okay, but having learned differential calculus, I just take f dash of x. Okay, here whatever happens, it is 2ax plus b here, but here it is 2 into x minus x minus alpha raised to 1. This is the derivative of this into g of x, and plus g dash of x into x minus alpha bracket square, and you end up having x minus alpha at least present once in both these terms, and therefore f dash of alpha is also going to be equal to 0. समझते का? So f dash of alpha is also going to be 0, equal to 0. And that confirms that alpha is a repeat root of this coincident root. Now, let us, alpha is a value of x. Alpha is a value of x, and we want the relationship of a, b, and c to get repeat root. So what we do now is we solve f dash of x and f of x simultaneously to eliminate x. Check whether you can understand this. Whether you understand this. 2ax plus b is equal to 0 is f dash of x, and ax square plus bx plus c is equal to 0 is f of x, and we want x out of these two equations. So I get x is equal to minus b upon 2a here, which I substitute here, a inside bracket minus b upon 2a bracket square plus b inside bracket minus b upon 2a plus c should be equal to 0. And now if you simplify this, what you get is b square minus 4ac is equal to 0. Array, cross check. 2a square, 4a square. Suppose if you make denominator, or it is 4a. So suppose 4a, if you throw it to RHS, you multiply c by 4a, and you have b square minus. Are you getting this? Are you getting this discriminant? So this is important. This is theory of quadratic equation. We got this discriminant earlier by completing square, but that was the local method useful for quadratic equation. What we are discussing right now, if you are interested in repeat root, you solve f of x and f dash of x simultaneously to eliminate the root constant that you want. Okay, here x is equal to alpha. Alpha was our root, and we wanted to eliminate x. Now, okay, this can be achieved one more way by using Rolle's theorem. Alpha, let alpha comma beta be roots of f of x. Okay, and f of x is a quadratic equation. Therefore, f of alpha is equal to f of beta is equal to 0. Both the roots are equal, and this is polynomial, therefore differential and continuous between alpha and beta. Suppose alpha and beta are the two roots. Therefore, we can apply Rolle's theorem. Rolle's theorem will say that there exists some gamma. There exists some gamma belonging to what? Alpha comma beta, such that f dash of gamma is equal to 0. That is what we will get eventually by applying Rolle's theorem. I am just showing you one more way of doing it. Alpha dash f dash of gamma is equal to 0, and as beta tends to alpha and gamma is supposed to be between them, then if you have repeat roots, f of alpha is equal to f of beta is equal to 0. That is one condition already you have. And as beta tends to alpha, basically alpha coincident with beta coincident with gamma, and therefore f dash of alpha is equal to 0 is yet another condition. This is one condition for repeat root, and f dash of alpha is yet another condition for repeat root, which we are trying to just understand by getting b square minus 4ac in case of quadratic equation. Now, what we are looking for here is you have here what you are looking for here is you have f of x comma y comma c is equal to 0 as a solution of differential equation. Okay, and we are looking at values of c where we are taking them very close to each other, and it is almost repeat root type of situation c. Okay, so f dash del f by del c with respect to c, you want to eliminate c out of it. Here we wanted to eliminate x, therefore we differentiated with respect to x, and we got eliminated, and we got the condition for repeat root. Now if we want condition for repeat root in case of solution of differential equation, anyway f of x comma y comma c is 0, that is 1, and second what we wish to do is differentiate the function with respect to c. Now because there are more than one variables here, partially differentiate with respect to c and equate it to 0. So if you use these two conditions, f of x comma y comma c is equal to 0 and del f by del c is equal to 0, you solve them simultaneously, you should get the singular solution, because this is what is the theory behind it. Now we go back to our original equation. Our solution of differential equation was this. What is our derivative with respect to c? So this is f of x comma y comma c is equal to 0. Eraser. Minus 1 is equal to 0. This is our original solution of differential equation. If we differentiate it with respect to c, can we do that? What is f dash or del f by del c? With respect, keeping x and y constant, what we get here is 2 x plus c is the derivative of the first term, derivative of y square is 0, everything is 0, okay, is equal to 0. 2x plus 2c is equal to 0, x is equal to c, or c is equal to minus x, admit, okay. So if we put c is equal to minus x in the given equation, we get x minus x bracket square plus y square minus 1 is equal to 0, means y square is equal to 1, and hence y is equal to plus 1 is our singular solution. So this is going, when you are trying to eliminate c, c is out of the picture, and what relationship you are left with is bound to be singular solution, because it is going to satisfy the original differential equation. You are processing the origin solution of original differential equation only, and you are finding out, this is called c-discriminant. Okay, and because the equation is not known to us, when we say c-discriminant, we mean f is equal to 0, or fx comma y comma c is equal to 0, and del f by del c is equal to 0. We mean this. You simultaneously solve these two, that is what you are finding out c-discriminant. That is what you are getting c-discriminant working. The way we have found out discriminant of this quadratic equation here by solving f dash of x and f of x simultaneously, we got this discriminant. What does this do? It gives you repeat root. It gives you repeat root. And alpha was repeat root in quadratic equation, we got it. Now, this theory works exactly over here because this is the solution of differential equation and this is what is the derivative, and you are considering 2 points which are very close to each other, and therefore that will give you the singular solution. Hope you have understood this. I wait for some time. Find the envelope. That is what is the problem. Find the envelope of x cos alpha plus y sin alpha minus k is equal to 0, where alpha is a parameter and k is constant. K is fixed. I mean, you can take 10, 5, whatever. But then this you have to look at it as f of x comma y comma alpha is equal to 0. This is a solution of some differential equation which we have not found out yet. I mean, we are not interested in that. Suppose we solve the differential equation and we get a general solution like this, and your constant of integration is alpha, which is sitting here, which is giving you family of straight lines, whatever these straight lines are. Then you find out f dash and find out the curve, find out the envelope. Two neighboring curves, when their values of constant differ by very small amount, they are called neighboring curves. And these two neighboring curves will intersect at some point, like in this diagram they are intersecting here. And as you make difference between those two values lesser and lesser, in limiting case, this point of intersection is called points of ultimate intersection or characteristic points. Okay, and this locus of these kind of characteristic points or ultimate intersection is called envelope. So envelope is a very special curve in the case of solutions of differential equation. However, I will just brief you about some additional things which are going to happen. Say for example, we have drawn this curve. Okay, so equation of this curve f of x comma y comma c is equal to 0, and you end up having a point here where one arm is going to give you this tangent and another arm is going to give you another tangent. So curve intersect itself, and therefore if we try to draw our integral curve, we will not end up getting any information here, because the curve intercept itself at that point and we will not be able to draw that small segment which represents the slope of the point of the curve. So this kind of points, they where the curve intersect itself, is called nodal points. Okay, and without getting into much theory about it, f of x comma y comma c is equal to 0, del f by del x is equal to 0, and del f by del y is equal to 0. If you solve these three guys simultaneously, you will end up getting all nodal points. Example, we had y square minus x inside bracket x minus a bracket square is equal to 0, a greater than 0. This was the equation of this kind of curve where a is this point, a comma 0. Okay, so this relationship LHS, if we consider it as f of x comma y comma c is equal to 0, then we find out del f by del x. Del f by del x means keep everything else constant except x. So del f by del x in this case, I will write down because I have little less time. X minus a into a minus 3x is equal to 0. So this is del f by del x, and del f by del y is equal to 2y is equal to 0. So if we take these three equations simultaneously and solve them, we get x is equal to a and y is equal to 0. That is the point where we have confusion about the tangents, and that is what is your nodal point. So I am telling you just the trick to find out the nodal point. The solution of differential equation that you have, or not necessary solution of differential equation. We were studying the curves earlier also. Before integration, we studied many curves, and suppose we wanted to find out if the curve intersects itself or not, do this activity and you will get it. Now, if the curves are of this nature, but then suppose this is one of the solutions of differential equations, and we have some constant introduced somewhere in between here, then we may end up having family of solutions like this. Now forget about that example, but suppose you have a curve like this, you have another curve like this. For different values of c, you keep getting different curves like this. Of course, they will look alike, they are same. So if you join these points, color red, these points, because that those locus of those points also will be there with the family, it's called nodal locus. It has nothing to do with the solution of differential equation. This locus, even if you are able to find out the equation of this curve, it will not satisfy the original because it's a confusion stage as far as tangent here, and the curve has got tangent somewhere else. So this nodal locus will not satisfy the original equation. What are the other cases that we may have? We may have, say, a curve like this where there is a cusp, C-U-S-P, sharp point. If you look at this arm of the curve, it is properly differentiable. So there will exist a tangent at this point for this arm. There will exist a tangent at this point at this one. So for both these curves, the tangent is the same. But as far as differentiability at this point is concerned, it fails because you will not be able to draw tangent at this point, okay, because it is a sharp corner over there. However, with the different values of c, you may end up having a family of curves looking like this, and there will be cusp at every family. And then if you join all these cusps, then you will get cusp locus. cusp locus. Again, this cusp locus is not going to satisfy your original differential equation. However, this whiteboard has stopped moving. Is it loaded? Okay. There is one more locus which I just want to just tell you. It has nothing to do with our syllabus, but it has something to do with the partial derivatives and arriving at those curves, which we are not doing. But then you need to know what is nodal locus, what is nodal point, what is, these are singular points, these are special points on the curve. Cusp locus, this, and the third is tack locus. You have a loop like this. Actually, I have drawn that, and then you have another loop. For some other value of c, you have another loop like this. For some other value of c, you have another loop like this. For some other value of c, you have another loop like this. Okay, and all of them are same. I mean, I am not allowed to change the nature of the loop. I am just changing the value of c, so I am allowed to pan them here and there. I don't want to change them. So now what will happen here is, at this point, there is a common tangent between the two curves. This is the curve for some value of c1, this is the curve for some value of c2. They belong to same family, and at some point, I mean, there will be values of c1 and c2 such that they share a common tangent. And now I have drawn it like this, but you can imagine that for distinct values of c, everything is occupied, and therefore there will be vertical lines which will be common between the two curves. And then this particular point is important, this point is important, and it is called tack. They touch each other, they touch each other. And then if you have a locus of these points, it is called tack locus. Okay, as far as this curve, these curves are concerned, if I draw a curve like this, where neighboring, this is going to be envelope. Tack locus is not going to be the envelope. Tack locus will not satisfy the differential equation. So these are the three different loci, and the fourth one is envelope. And we have understood how to find out envelope, because that is what you might require in physics also, finding out the projectile motion. If you try to find out the envelope in this method, f of x comma y comma c is equal to 0, f of, and del f by del c is equal to 0. If you do this, you will get the envelope there also. So these are the singular points. Which are singular points? Nodal point, cusp, tack, these are special points, and these are special loci, basically nodal locus, cusp locus, tack locus, and envelope. These are the special, all of them are singular, one of a kind, special, has nothing to do with the family, will not have any constant involved in it. That is why they are called singular. And one of the singular point locus that we have happens to satisfy the original differential equation. Therefore, we call it as singular solution. Okay, and f of x comma y comma c is equal to 0, and del f by del c is equal to 0. If you solve these two simultaneously, you will not miss any of the singular solutions. Any of the singular solutions. Okay, that is what is the theory that I want to tell about the differential equations. This is much beyond what we are required in IIT. IIT, you are required to solve problems, which you should solve from whatever source you get, solve all possible differential equations. And that is what I conclude this theory and discussion that we have for differential equations.